Good morning, good afternoon, and good evening, depending obviously on where you're watching us from. Thank you for joining us and welcome to Dr. Graham's Blow Up Science. This is, of course, a show that is presented as part of SciFest Africa, South Africa's National Science Festival, the 24th celebration. And of course, this year we're doing it over 6 months and online. Hope you've been enjoying all that we have had to offer so far. If you've missed any of our shows, please go up onto our website and look up on the page that has past and present events, which is events to come, obviously. I'm really excited about this morning, this evening, if you are where Dr. Graham is, because I am expecting quite a lot of blow up. Actually, if we go to the blurb if we just were to read through that, you would see that questions were posed. Can you really launch marshmallow out of a vacuum cleaner, make rockets from common household items, or run an engine on liquid nitrogen? Prepare yourself for some serious mind-bending science as Dr. Graham explores his way through the chemistry and physics of things that bubble, boom, bang, and occasionally catch on fire. With loads of audience involvement, laughs, excitement, exciting experience, brain-rattling explosion, and learning, this action-packed show is a celebration of the fun in science. Yes, this morning we will be celebrating the fun in science, and Dr. Graham will help us do so. Dr. Graham is actually a long-time friend of SciFest Africa. He convenes the Master of Science Communication Outreach Program at the Australian National University. His current research and engagement investigates international capacity building and co-design in science communication. To this end, Graham founded the Australian government-supported Science Circus Africa project, which has trained 499 staff and reached 73,000 people in 10 African countries. Graham also researches emotional and motivational aspects of science communication, particularly in settings like science centers, science shows, and hands-on workshops, and using these methods to engage with social and environmental issues, along with teaching in these areas. He is an avid aficionado of science shows and has performed shows and delivered training globally. He very much misses SciFest Africa and can't find a vuvuzela anywhere in Australia. Dr. Graham, thank you so very much for honoring our invitation and setting aside time to be with us this morning. Really excited for the show, and really thank you very much. Over to you.
Great. Thank you. Thank you, Freddie, and thank you everyone for tuning in. Thank you for that very generous introduction. I am devastated that I can't be in Grahamstown in South Africa over on your lovely continent, but this is the next best thing. And while there's been a lot of difficult things this year, it has brought us together in some strange ways, and this is one of them. So today I'm going to talk to you about blow up science. So some things will blow up, and there's going to be some things that you can try at home. There's going to be a whole lot of things you really shouldn't try at home, okay? So if you're watching this on the live stream or you're watching it later and you're like, whoa, I might go and try that, just be careful because there's plenty of things you shouldn't try at home, but I've made sure that there are some things you can try at home, and always safety, safety, safety first with science. So we are going to do some blow up science. And during the show, I'd encourage you to use the chat or the Q&A to interact. I might ask you to make a prediction. You might have a question. You might think something was awesome and you want to tell everyone. Please feel free to pop some comments or questions in the chat, and we'll have a whiz through them at the end of the show. But we are going to talk about some blow up science, and just with really common things you find around the house, you can usually do some blow up science, okay? So all I've got here are things that might be in your kitchen right now, just some vinegar and some baking soda. And when they mix together, they do more than mix, they react. And in that reaction, that chemical reaction, they make some bubbles. And those bubbles are what makes it blow up. Those bubbles create something called pressure. So whether you're pumping up a football so it's all hard, that's pressure. Pumping up a bike tire, pumping up a car tire, making bubbles inside one of these little containers. Everything's getting squashed together. Big idea here, pressure. Okay, lots of things will blow up if you put too much pressure inside them. And we're going to use that for a whole lot of things today. The other thing we saw, that once we've got that pressure, you imagine there's these bubbles in there, or it could be the air inside a football, and it's pushing on the inside of the container or the inside of the football. So wherever we've got pressure, we've got pushing. So we've got a force. And a force, just a fancy word for a push or a pull. But we've got a pressure making force. And you probably know what happens when there's too much force, stuff starts to move, okay? So we've got motion. So the big science ideas we're going to be looking at today are pressure, like all the squashed bubbles inside there, forces, the push it made, which pushed the lid that way and the container up the other way, and of course movement or motion, okay? And I've got a nice little mark on my roof, the joys of working from home, okay? Now, this is a lovely little experiment you can try at home to make some pressure, force, and motion. Make sure you come equipped with some eye protection, and if you're a young scientist, also a grown-up. Now, should we do that again? And look at this. I've actually managed to use one rocket to knock my other rocket down. But you can make a rocket from common household items. You just need a little bit of vinegar, not too much, and a little bit of baking soda. Now, we used to do this experiment with something called a film canister, and they become very rare. But often in science, and especially in engineering and design, we have to think about, well, what are the other things that could do that same job? And as long as you can find a container that has a pop-top lid, then it will hold the pressure. That pressure will build up. Once that pressure is too high, it'll create that force and that motion. And you'll find there are heaps of kind of containers that have this property. Okay, so it might be yogurt. These ones are from some vitamin tablets. These ones are from some medicine. So any pop-top container, you can try this at home. Remember your eye protection. Should we try the big one? Yeah. Should we try the big one? And if you do try this at home, love it if you could post a little video to the SciFest Africa Facebook page so we can see your results. Now, this one's slightly bigger and the lid goes on a lot tighter. So the pressure is going to be higher, and it also means our force and our motion is going to be higher too. So it might take a little bit, whoa, we're going to go up, and off it goes. So pressure, force, and motion. If you want to understand how something blows up, there, some of the science you're going to need. Now, that was a lovely little experiment, but I've got a feeling some of you out there, you know, you're expected not just things blowing up, but things blowing up and catching on fire. Would anyone like to see some of that? I thought you might. So we're just going to clean this up because we don't want fire and water. It might put it out. And we definitely don't want fire and the little bubbles that we made. The little bubbles the vinegar and baking soda make are carbon dioxide. And you can actually put a fire out using carbon dioxide. You'll find it in fire extinguishers. To make a fire, we need a different gas. And the most important gas, if we're going to create a fire, is oxygen. I've got some in this container. The other thing we need, so we need oxygen, we need fuel, and I'm using some natural gas here, and we need some heat, which I'm going to get from that. So they're the three things that we need to make a fire. Take any of them away, nothing's going to blow up, but we've got all three of them right here in my spare room. So I have put some oxygen in the bottle, and you'll notice that there is a little hole right at the end. Okay, we're going to pop that in, and I'm going to make a little fire inside this bottle, and we're going to blow something up with it, because this is blow up science. Now, I'm going to take one of these. You might know them too. Tasty. Okay, we've got our little marshmallows, and we're going to pop a marshmallow into our marshmallow bazooka. All right, in it goes. And we're going to need not just our pressure, force, and motion, we're going to need some maths. Now, hands up or comment in the chat if you don't like maths. Now, I'll be honest, when I was a young scientist, maths wasn't my favorite subject, but now I've seen how useful it is. I've really changed my mind. We can put maths together with so many things. So whether you want to be a stockbroker or a trader or just about anything, you're going to need maths. And to do this, I need to put my maths together with my chemistry. So the maths can help me work out how much fuel I need, and the chemistry tells me the ratio or the balance I need it in. Because chemistry, it's a lot like cooking. We need all the ingredients in the right balance. So if you're making up a batch of Cook Sisters, you need everything in the right balance or the right ratio. And chemistry is just the same. Using my maths, I can work out that this is just the right amount of fuel for the amount of oxygen I've got in the bottom. This is a reaction between the fuel and the oxygen. Now, I'm going to attempt to shoot this at the webcam. You're like, Graham, that sounds like a bad idea, but only if my aim is bad as well. So let's try it. 3, 2, 1. Woo! Okay. Now, I don't know if you saw that coming. It was coming pretty quick. The first observation I've made is that this bottle's nice and warm. So something did blow up inside, okay? That fuel's burnt. As it burns, it creates lots of hot gas. And that hot gas is actually too big to fit in this container, which means it's squashed down. That's what we mean by pressure. And because it's squashed in here, it wants to get out there. And as it gets out, it pushes our little marshmallow out of the way. Now, that was a lovely little demo. And I'm going to show you a slightly bigger version. Would you like to see a bigger version? You would? Okay, don't try this at home. Now, I've got a slightly bigger version. And this actually shows us one of the places we use this science. And this is not just science you'll see in Dr. Graham's blow-up science. This is science you use whenever we're in a car, okay? Inside a car, in the engine, we've got lots of things that are this shape, okay? Lots of things that are this shape. And those things are cylinders, okay? You might have a 6-cylinder car, a 4-cylinder car, and inside the cylinders, each one has a little spark plug. Now, I don't know if you'll be able to see this, but oh, look at that. You can see how dirty it is inside my cannon, but you can also see a little spark. Did you guys see it? A little tiny spark. That's going to provide the heat for this reaction. Okay, to start this reaction. So we've got fuel. We're going to get the fuel out of here. Okay, I'm using a mixture of our natural gas mixed with another fuel that I really like called ethanol. You can make it from plants. Much better for the environment than a fossil fuel, but still not as good as some of the new hydrogen technology. But that's a bit too exciting to do here in the spare room. So I've got fuel, oxygen, and heat. So I can make a fire, I can create pressure. I think I'm just going to need something for my cannon. Okay, so we'll grab one of them up. Oh. It looks like these marshmallows are a little bit too small. So I'm just gonna have a look down here at potentially some other things I've got that I could put in the cannon. You got any ideas? Any ideas out there? Oh. No. Oh. Do you want to put the Angry Bird in the cannon? I think you do. Okay, we are going to put the Angry Bird in the cannon, all right? And this is a really good time to remember that good science is safe science. And staying safe means thinking about the risks. And it's best to think about them before they're actually happening, okay? So we're going to assess the risks. Do you know what I'm worried about? What we're going to do is we're going to stick this Angry Bird into the cannon. We're going to blast it across the room. So I'm a bit worried about some of the things in the room, but I'm most worried about this bird. I mean, have a look at this bird, ladies and gentlemen. Have a look at this bird, okay? He's already angry, right? Born angry. We're going to stick him in the cannon. We're going to create a huge amount of pressure and fire behind him, and we're going to launch him across the room, okay? So we're going to have a lot of pressure. We're going to have a very, very angry bird, okay? Now, I am worried about how angry the bird's going to get, but I have to tell you that you don't want to see how angry this bird gets when its bottom catches on fire. And you can see it's happened before, okay? It's very dangerous. So we're definitely going to do a little bit of wonderful science to protect our Angry Bird's bottom. Now, this glass of water, so refreshing. So refreshing for me, but also refreshing for our Angry Bird's bottom, okay? Now, you might think, Graham, but this is scientifically rigorous, boys and girls. Water is very, very good at absorbing heat, can take in lots of heat, but it doesn't heat up much itself. It takes lots of energy to heat up water. This makes water really good at cooling. And in fact, in a car engine, like we were talking about before, we use water to cool it down, just like we're going to use water to cool down this Angry Bird. Okay, so everyone ready? You ready at home? All right. So in goes our fuel. In goes our Angry Bird. Okay. Pop our Angry Bird on there. Pop these on here. Does he look angry? So angry. Let's do it. Let's have a little countdown up there. 5, 4, 3, 2, 1. Ooh. Okay. Wow. Now, I can feel in there and it's really, really warm, okay? We've burnt the fuel. We've created lots of gas. And because the gas is trapped in there behind the Angry Bird, the pressure gets higher, the force gets bigger, and eventually it pushes our Angry Bird out of the way. Now, pushes it out of the way, and you might have even seen the fire. Did anyone, if you saw the fire, or if you missed the fire, maybe just pop something in the chat, because I don't want anyone to miss the fire, because it's exciting and it's the heart of what's going on here. And I'm just going to check. Just give me a second. Someone out there in Chatland has said they missed the fire. So what we're going to do is actually show you that fire a little bit more carefully, okay? And this would be on the list of things not to try at home under any circumstances. Now, we are going to see that reaction, that wonderful reaction that has been fueling our cannons. And I thought, since this was blow up science, I would get a little bit hands-on. You shouldn't do this. Don't try this at home. But I'm going to do a little bit hands-on. I'm collecting some of these fuel in some bubbles. So these are not the normal kinds of bubbles you have when you're washing up. Or if you do, be really careful with those bubbles. These bubbles have different properties, okay? Wow, I just saw my webcam just totally maxed out on its white balance, but you would have seen the fire that time. And if you didn't, I'll bring it back a bit more. And you notice that a tiny amount of fuel makes a lot of fire, okay? It makes a lot of fire. And that's where our pressure comes from. Whether it's a car engine or whether it's my rocket in here, it's making a lot of pressure. Now, you might look at that and go, that's great, Graham. And I know how cars get around, and I saw the marshmallow cannon. This blow-up science is pretty exciting stuff. But one of the things I love about science is that once we understand science and once we understand what's going on, we can use that, okay? We can use it to solve problems in our lives, in other people's lives. And for me, that is what science is about, okay? It's about using these ideas to help people. And if you look at the amazing progress that we've made on the COVID vaccine in such a short time, it's a real testament that science, especially when science works as a team, that it can really achieve great things for humanity. And I thought about this and I thought, well, what could I do with this blow-up science? What amazing invention could change the world? And I made this. I'm going to bring it a little bit closer. Okay. All right. Now, this is my Marshmallow Bazooka powered Barbie car. Okay. You might not be able to read the number plate, but this is a Barbie car. And it's pretty good to give us an idea of the kind of things that we can do with the science, but also some of the other forces that are involved. Now, you saw with our other marshmallow cannon, you saw that there was a force that pushed out the marshmallow that way. Now, I've got a question for you, and if you know the answer, pop it in the chat. If I push something that way, is there another push, or is it just the one that way? Now, if I put the car on wheels, we might be able to actually see. If I push something that way, will we get another force, okay? Now, if I push myself off the wall here, the wall makes a force on me, I make a force on the wall, I get pushed away. So when we push the marshmallow out of here, we actually get another force this way. And you might have heard people say, well, every action, it's got an equal and opposite reaction. That's one of Newton's laws. So if we push a marshmallow that way, we should get some motion that way. Now, you might be looking at this going, Graham, that is a very, very big marshmallow bazooka, and you're planning to put these very, very big marshmallows in there. Have you thought about the risks involved? And I want to tell you, SciFest Africa, that I have. I'm in my little spare room, but safety first, ladies and gentlemen. Here we've got a giant landing net to catch this priceless work of invention. So we're just going to set this up here. All right. That's lovely. All right. Lovely. Okay. Look at that. All right. Risk assessed. So I've got my Canon buggy. I've got my safety net. Just pop that on there. Just some little delicate adjustments going on down here. Okay, lovely. Now, I was thinking of just putting one marshmallow in, but I thought you might want two. Does anyone want three? Do I hear three? Do I hear three? Three. Okay, we're going to put two in. Should we do three? Okay, we'll do three. All right. Where are my giant marshmallows? They are enormous. Okay, giant marshmallows are in. Now, the other thing I need to put in is the fuel. And this is where our maths comes in really handy, okay? This bottle is about 15 times as big as the other one. So, with what I know about chemistry, I know, well, if I've got 15 times as much air, I've got 15 times as much oxygen, therefore, I'm going to need 15 times as much fuel. And that means 5 of these really big ones, okay? So in it goes, and you can just count along at home. 1, 2, 3, 4, 5. So what we've done there is we've just basically doubled the recipe, okay, or 15 times the recipe. If you've ever been cooking at home and you've got a recipe for 4, but you've got 8 people, you just double everything. And we've done exactly the same thing here, okay, but we've times everything by 15, which means I definitely want a pair of these. Okay, now what we're going to do, we're going to light it on this end. Now marshmallows are going to come out of that end, and I want you to look if you can see evidence of any other forces as we go. All right, everyone ready? 3, 2, 1. Ah, yes! Now, I don't know that these Barbie cars are going to catch on, and we're going to need an awfully big one to get me to work. But it does show us that with creativity, understanding our science, we really can come up with amazing inventions. And especially you young people out there, some amazing inventions come out of the youngest people, and some amazing inventions come out of South Africa and Southern Africa. So don't let anyone ever say that you can't come up with amazing ideas, because you can. They're probably even better than that Barbie car. Now, been doing a whole lot of pretty good blow-up science, and for my next experiment, I'm going to do something that it's going to be tricky. It's going to be tricky, ladies and gentlemen, because the piece of scientific equipment that I've decided to use to blow something up does the complete opposite. It's an unblowing machine, okay? It unblows, and I'm going to try and blow something up with it. So this is going to be tricky. And the unblowing machine, it's pretty exciting, okay? It's pretty exciting technology, direct from the university. And I'm going to get it out in a second. And if you've never seen one of these unblowing machines, maybe some of the lab scientists might have seen one, I just want to prepare you, okay? Because it really is pretty exciting. So, ladies and gentlemen, boys and girls, if I can get everybody at home or wherever you are to give us a bit of a drum roll. I can hear it all the way from Canberra. Keep that drum roll going. Ladies and gentlemen, the unblowing machine. Ta-da! Now, I can tell a few of you are not taking this seriously. You're like, is this guy a doctor? Is this guy qualified? Because he just has revealed this unblowing machine and he's going to try and blow something up with it, okay? Now, you might know your vacuum cleaner or you might know your unblowing machine as a vacuum cleaner, but that's what your vacuum cleaner does. It makes pressure, but it's not the kind of pressure that we've made before. Inside here, everything was really squashed together and we call that high pressure, okay? If the opposite of high pressure is low pressure, and that's where everything, in this case air, is kind of extra spread out, okay? It's extra spread out, and that's low pressure. And that's the way your vacuum cleaner works. It makes a low pressure in here, and the normal pressure outside, what we call air pressure or atmospheric pressure, it's higher. So the air will always go from where the pressure is higher, like out here, to where it's lower, in here. And so the air goes in. Now, what I'm going to try to do, because this is Dr. Graham's Blow of Science, is actually use this vacuum cleaner to launch a marshmallow. Now, a few of you are probably sitting there going, Graham, it's just not going to work. The air is going the wrong way. And if I put a marshmallow there, I think we all know what's going to happen when we turn it on, okay? Because that's the way the air goes in a vacuum cleaner. And just to prove to you that it does that, we'll just turn it on. You might be able to hear it. So you can see it pulls things in, okay? The air is definitely going in. Can you hear the air going in? Can you hear it? Yeah. Yeah. Ooh. So the air is definitely going in, which means if we want to blow something out of this, we're going to have to come up with another one of those inventions. Now, I really wanted to do this in my show because the very first time I discovered this invention was in South Africa on a visit over there to come to SciFest and to visit some very good friends in KZN. And they showed me an invention, which, as far as I know, is a South African invention called the Marshmallow Bazooka. Now, there's lots of different ways you can make one, but I'm going to show you a really easy way, and you can do this at home, okay? Get a piece of pipe, cut the end off like this, get a grown-up to help you, and then get another bit that is one of these T-shaped connectors, so you can build it like that, and then you're going to need a little bit on the end to stick onto your vacuum cleaner. Now, the last thing that you need, and you might have noticed it, is this little door here, okay? You see this little door? This little door is really important. You can just make it from an old bit of plastic or a postcard or something. You'll see how important the little door is in just a second. Now, I'm going to attach this to my vacuum cleaner, and you might look at it and go, Graham, it's not going to work, okay? It's not going to work. All you've done is put a really weird set of tubes on the vacuum cleaner. It doesn't change which way the air goes, okay? So let's try it out. So even though the air is going out, even though the air's, going in, our marshmallow flies out. And if you have a look at where the marshmallow starts, how the door closes, and which way the air moves, it all starts to make sense. As soon as I turn the vacuum cleaner on, the air wants to get inside here. So it actually pushes the door closed from the outside. Remember, pressure can push things. Pressure can make a force. Once that's closed, all of the air is going along here and down there, okay? And once I put the marshmallow in the way, that air pushes the marshmallow along. Now, when the marshmallow gets to here, it's going so fast this way, it keeps going the same way. And that is another one of Newton's laws, okay? Once something's going fast one way, it'll keep going that way until another force acts on it, okay? Now, what we're going to do is we're going to try and shoot some of these at the webcam. And if I catch anyone putting their mouth up on their TV or on their screen trying to catch these, there will be trouble. Sci-Fest trouble. Whoa! Now, a few of them were pretty close. I'm not going to try and knock the webcam off. Not that that's happened before, but it just shows whether we've got high pressure or low pressure, we've still got forces, and wherever we've got forces, we can get things to move, okay? And a lovely bit of blow-up science that you can try at home. Lovely. Now, ladies and gentlemen, you might have noticed it is the end of the day over here in Canberra, Australia, and it is heating up, okay? Not just with climate change, but it's just a hot day over here. And I thought, well, I'm doing all this blow-up science, things catching on fire and getting hot. It's getting a bit steamy in here. And I said to my friends at the chemistry department, I said, have you got anything that could cool me down during my blow-up science show? And they gave me this, okay? What I've got in here is some liquid nitrogen. It's very, very cold. It has amazing properties apart from being cold. And it's also pretty good if you need to blow some things up. So we're going to do that. Let me just get a few things out. Now, liquid nitrogen is very, very cold, okay? So we can use it to freeze things, but this show is not called Dr. Graham's Freezing Science. It's called Blow-Up Science. So we're going to have a look at some of the other properties of liquid nitrogen that make it good for blowing things up, okay? We're going to see how nitrogen can create pressure. All right, let's have a look at some of our nitrogen. Now, before I put some in here, one of the things that I don't like about doing these shows on Zoom and Facebook is that we can't have that great interactivity, okay? And usually, you know, there's lots of chatting, lots of interactivity, and we can still ask questions, so pop them in the chat. But the big problem with this kind of show is there's no giveaways. Anyone out there want giveaways? Yeah, I thought you might. So I'm actually going to do a very special Sci-Fest Africa giveaway direct from the Australian National University, okay? At the end of the show, I'm going to pick the best question, and I'm actually going to post some liquid nitrogen to that person, okay? So you can do some experiments at home. Now, we're going to get some of the liquid nitrogen out, and we're going to do this giveaway. Now, a few things you've probably noticed about the liquid nitrogen is that it kind of makes this cloud or this fog. It's super, super cold, okay? And it's so cold that it'll turn your breath into a cloud, okay? If you're up walking, say in the Drakensberg or, you know, down in Cape Town up on Table Mountain and it's a cold day, you might have seen your breath, okay? You see your breath when moisture, that is a gas, water that is a gas in your lungs, turns into a liquid. What you're seeing there is liquid water, okay? It's not smoke, it's fog. And the liquid nitrogen is cold enough to turn that gas in my breath back into a liquid, okay? Back to our giveaway, okay? Almost got distracted by all that science. Now, I'm going to pop this liquid nitrogen into this. Oh, it's approved. Look at that. Into this container. And just a few safety tips for whoever wins the liquid nitrogen. Remember, gloves, goggles, adult supervision, and to keep the lid on, okay? Because if the lid falls off, you could, see, you could spill it. And that could be dangerous because this liquid is minus 200 degrees, okay? Super, super cold. So whenever you're using it at home, when you finish, just pop the lid on to keep it nice and safe. Now, I didn't expect that to happen, and I seem to have lost my lid somewhere here in the spare room. Oh, no. Here it is, up on the bookcase. But I'll pop the lid on, and we'll get this giveaway. Okay. Now, you can see that this is not going so well. And a few of you out there, you're like, I really wanted this giveaway to happen. But every time I pop the lid on, and I'll bring it a bit closer, every time I pop the lid on, you might notice even a force pushing the lid off. You might notice it starting to bulge a little bit. What? Did you see it bulging? Kind of bulging at the top. So something is pushing, is making a force on the inside of our container. Now, if I can try and find the lid, we will try that one more time. No, we won't, okay? You saw the pressure build up and that pops the lid off. And I'm really sorry. All my SciFest friends, but there's no way that they're going to let me put this in the post and send it to South Africa when it's exploding like that. And the worst thing is that not only has it been blowing up, when I see how much nitrogen is left, it seems to have disappeared. You might have noticed it is really cold on the bottom. It hasn't leaked out the bottom. Apart from that, there are no holes except the top of this container. This nitrogen has leaked out the top. And when it did it, it wasn't a liquid, it was a gas, okay? It can change into a gas. And that is what was making our container blow up and wrecking what was otherwise going to be a very lovely giveaway. Now, liquid nitrogen does some amazing things. And one of the things it can do is boil at room temperature. I'm going to bring that up nice and close. You can all see what it's doing. You can all see what it's doing just there, okay? It is bubbling, bubbling, bubbling away. It's actually boiling, okay? It's boiling. So we're used to things like water, which boil at 100 degrees, okay? Liquid nitrogen boils at a much lower temperature, at about minus, so below zero, minus 196 degrees. So it will boil like absolute crazy at room temperature. And when it boils, the liquid turns into a gas, okay? As it does that, it gets bigger, all right? In the liquid, all the little bits of nitrogen, the molecules of nitrogen, they're all, whoa! They're all tightly packed together. And usually our balloons get a little bit bigger, but this is some enthusiastic blow-up science. When they're a liquid, they're all tight together. When they're a gas, the molecules of nitrogen spread out. And that means a little bit of liquid makes a lot of gas. Now, ladies and gentlemen, I can see from the disappointment in the chat, I can see a few people going, Graham, that balloon was not high quality blow-up science. Would anyone like me to try and blow up another balloon, but do it properly, okay? You can't trust an Australian, okay? Especially cricket, rugby, and blowing up balloons. You've got to keep an eye on us, okay? Now, I'm going to get another balloon out of here. There we go. And we're going to try and do some even more exciting blow-up science because I think we can get that balloon a lot bigger than that. So let's put this on. Now, the liquid actually expands by maybe 600 or 700 times. So a tiny bit of liquid makes a huge amount of gas. So we actually should see, with just this small amount of liquid nitrogen, we should see the balloon get much, much bigger. So let's get some more nitrogen out. So nitrogen's always boiling away. We're going to pop a little bit more nitrogen in here. We'll see if we can get some slightly more impressive blow-up science happening. Pop our cork in. You notice the cork even blew itself out, just in the spirit of the show. So here's our liquid, here's our gas. The reason our balloon is filling up is because the liquid is boiling, turning into a gas. As it does that, all of the bits spread out. So a little bit of liquid, you see it's only this high, makes an awful lot of gas. Now, you don't have to at home, but I'm going to block my ears because when this balloon explodes properly, it's going to make some serious blow-up science. It may even max out the microphone. So if it all goes quiet, it was because the blow-up science was so awesome. Okay, and off it goes. You still see a little bit of that gas coming out now. So the pressure created as the gas builds up makes enough of a force to pop our balloon from the inside. And there are some super cute ways that we can see that force. Let's just, that being one of them, might have just noticed that our cork just came out. So we can see the pressure build up and apply a force to our cork. The other way that we can see that force, and this one, because SciFest, you know, it's a bit of a party, a bit of a celebration of science, especially for my friends at SciFest. Okay, so we can see the pressure build up and create a force to open up our little whistles, okay? Off. Okay, come on. Okay, so we can use the liquid nitrogen, and it's the way that it boils and gets bigger as a different way to make a force. Now, a really interesting thing to remember for your science is that we make pressure with both of these methods, but they're very different. When the liquid nitrogen boils and turns into a gas, it's still nitrogen, okay? It's changed state. So liquid to gas, solid to liquid, these are changes of state. Nothing actually changes. When we made pressure using our fire, we actually had a chemical reaction, and things do change. The stuff we put in is different from what comes out, okay? So this one, chemical change. This one, physical change, okay? Lots of different ways that we can blow things up. Now, I'm going to pour my nitrogen out, and we're going to have a look at one last application of this wonderful blow-up science. And what I've got here is another little invention, okay? And it's another great example that once we understand science, we can use it to create awesome things, okay? Like this liquid nitrogen-powered engine. Now, I didn't come up for the design with this. It was actually invented a long time ago. And if you look up Hero's engine on the internet, you can find some of the very first engines that people ever made used a design just like this. The one difference was that they used water rather than liquid nitrogen, because in the olden days, liquid nitrogen wasn't something you found that often. But just like water, it will boil and get bigger. So the very first steam engines that we made, steam trains, used this same idea, using pressure to make a force and doing it by changing something's state. And what we're going to do is use that exact same idea for our liquid nitrogen engine. Now, a couple of interesting things about our liquid nitrogen engine and something to start getting you thinking about the forces, okay? We've got a little tube here, and this tube points out that way, okay? We've got another little tube on the back that points out that way. Now, when I put the nitrogen in and put the lid on, all of that gas is going to come rushing out there. It's going to come rushing out there and rushing out there. I want you to make a prediction about what kind of motion or movement we might see. And I'm going to give you a clue. If we've got gas rushing out that way, maybe we're going to have another force. Remember this? So let's try that out. We're going to put a little bit of our liquid nitrogen in, and I'd like everyone to make a little prediction at home, okay? You can pop it in the chat. You can turn to the person next to you and make a prediction. Because in science, one of the things we do when we start an experiment is make a prediction. And by testing our guesses, it's that simple, is one of the ways that we create knowledge in science, okay? We make a guess and we test it. So everyone got a prediction? Wonderful. On goes the lid. I'm going to lower it into some water in here, and that water is going to help the nitrogen boil. It's going to be a source of heat. All right, should we try that again? A little bit more liquid nitrogen. Now, you might have seen that it started to spin, okay? Started to spin because as the gas rushes out of those tubes, it creates a force that pushes back on the bottle. I've got a little bit too much ice on the bottom there. Let's just get that out. Oh, I think we need a little bit more liquid nitrogen. Should we put more in? Should we put heaps in? Okay. All right, let's put heaps in. Going to put our liquid nitrogen in. I'm going to pop the lid on. I'm going to lower it into the water to get our engine going. Woo-hoo! That is a good one. One more time. In goes the nitrogen. Oh, need a little bit more liquid nitrogen. It's all boiling away. Now, often on the third one, we see something quite interesting. You might notice that a whole lot of ice has formed around the bottom, okay? And the ice actually kind of insulates it. So the liquid nitrogen that's inside is being kept cool, okay? Kind of like a thermos cup. It's keeping it nice and cool and means it doesn't boil quite as quickly. Might mean that we actually see a slower engine turn. Let's find out. Lovely, and you can really see that action, and you can see the fog pushing out, and it's the fog pushing out and the second force pushing back that gets our motor turning. So, lovely little bit of stuff we can do. Whoa! a little bit of a mess going on here. And that brings us to the very end of the show, and we will draw the curtains. Thank you very much, ladies and gentlemen. I've been Dr. Graham Walker from the Australian National University. It's been an absolute pleasure to come back to SciVest, albeit virtually. Can't wait till we can get back on airplanes and visit each other's wonderful countries, wherever you are in the world, and especially if you're on that wonderful continent as part of SciVest Africa. Please enjoy your science, do it safely, and remember to stay curious. Right. Thank you very much, ladies and gentlemen. Let's have a look at the questions.
Wow. That is really amazing. I'm just reading from the chats. And we saw the fire. Wow. Dr. Graham, why did your hand not burn?
Oh, this is a good question. Okay. Oh, someone saw the fire. Lovely. Okay. Wow. Here we go. From Karen. Dr. Graham, why didn't your hand burn? Okay. And this is a really good question. Okay. Not so. You can try this yourself because you really should not try this experiment at home. But I'm glad that finally there's a South African out there that is worried about an Australian. Okay. I've seen how you play rugby, and I don't think it comes through there, South Africa. but I'm thrilled that someone is worried about my hands. And you'll see both of them, they're just fine, okay? They're not burnt. And the reason was that I had some water on my hand, okay? The detergent that I've used to make the bubbles dissolved in water, and the water, just like we saw with our Angry Birds bottom, it keeps it nice and cool, and it keeps my hand cool as well. Now, I will just repeat, just because you know the science, there's a few other things I'm doing there to keep me safe. I'm not going to tell you what they are because you should not try that at home. Okay, who else have we got in the chat? Oh, my good friend Derek Fish. If you're up in KZN, go and visit his wonderful science centre in Richards Bay. And Derek has pointed out that the marshmallow cannon is a South African invention by a wonderful man, a man that sent me lots of boxes of stuff to Australia, called Professor Jeff Binden, I think from UKZN. So wonderful testament to South African innovation. See if we've got some other questions there. All right. Yeah, another question. Where is liquid nitrogen found? Now, on Earth, because of the general temperature, we don't find nitrogen in a liquid state, okay? It just doesn't get cold enough. So to make nitrogen turn from a gas into a liquid, we need to either cool it down to about minus 200 degrees or to change the pressure, okay? We can do that using big machines, but you won't find nitrogen in a natural kind of liquid state anywhere on Earth. There might be other places in the universe where it does get cold enough that you might have like a whole ocean of liquid nitrogen or something like that. But on Earth, most of the nitrogen that we encounter is not in a liquid form, maybe at a hospital or a science lab. It's a gas form. So if you want some liquid nitrogen, or sorry, you want some nitrogen to play with at home, you just go like that. And what you've got there in your hand is about 3/4 nitrogen. Okay? It's a very, very common gas, but not a common liquid. All right. Got any other questions here? Oh, yeah. Oh, where's liquid nitrogen found? Oh, here's a great question from Kiara. Thanks for writing in for your question. Kiara said, whew, it's got a bit cold in there. Why didn't the jug spin? Okay. And this is a good question. But I had some water in here to warm up my nitrogen. Okay. And this is just sitting in the water. So it can actually move quite freely, okay? The water kind of lubricates that spin as well as warming up, our nitrogen. So it'll all stay there. If I just put the jug like this, then maybe other things are going to start spinning, okay? A great question. Oh, a question from Derek. Why don't you use liquid oxygen? Okay, now you might remember from our experiments with fire that they need oxygen, okay? And there's a lot of oxygen in the air. It's about 20% oxygen. And it means that if you've got something flammable, like, you know, some wood or some fuel like we were using before, it'll burn really well. Now, if you move to liquid oxygen, then things you wouldn't expect to burn very well, like muffins or marshmallows, can become super, super dangerous, okay? They can burn incredibly well. So while that experiment, our engine would still work, forgot my cameras, while it would still work with liquid oxygen, it would get very, very dangerous. So knowing our science helps us understand what can be dangerous and what you just shouldn't try, like doing that with liquid oxygen. But a really good question from, thank you, Derek. Oh, how come the nitrogen is cold? Basically, just because it's been, to get our nitrogen gas into a liquid when they're making liquid nitrogen, which you're doing right now in South Africa, we take nitrogen gas and we squash it at the same time as cooling it down, and it changes from being liquid into a gas. You just watched it turn from a gas into a liquid as it heats up, and we can do the reverse, okay? So a physical change like boiling or freezing, all of those things, they can go backwards and forward, and it all depends on the temperature, okay? So as we cool nitrogen down into a liquid form, it will become very, very cold. Okay. All right. few other people. Oh, someone else asking, am I a medical doctor? Okay, not unless it's a real emergency. No, I actually, I'm a doctor of science communication. So you can actually study this kind of thing. And at the Australian National University, we have a place where if you want to, you can come and study science communication. The Australian government actually provide scholarships for master's level study for South Africans. So if you're keen on that, Google Australia Awards and you can come and study science communication. Some wonderful places that you can study science communication in South Africa as well. Okay, most of the unis are doing something. Down at Stellenbosch, they've got a centre for science communication and doing some wonderful work. So if there's some young people or some middle-sized people here going, wow, that looked like a pretty cool job to have, you can actually do this as a job, okay? But you do need to study. Like anything, you want the really cool jobs, you're going to have to study, all right? Any other questions on there? And did we have any questions come across from the Facebook?
No? There's comments saying, great show, wonderful, you're a legend. Thank you very much.
That's wonderful. And look, thank you for the very kind words. Everyone out there at SciFest Africa, I do look forward to where I can be there in person in your lovely big theatre where we can blow up even bigger things. But until then, tune in to all the other wonderful SciFest Africa events. If you want to find me online, you can find me on Twitter at Dr. Graham, so just DR and then GRAHAMS, and the same on Facebook. Or if you just Google my name, Dr. Graham Walker, find me on Twitter, on Facebook. If you've got any other questions or you want to keep up with what I'm doing in science communication, feel free to give me a follow. And if you have any other questions and things, I'll come back in on the recording of the live stream. And if you've got any other questions, feel free to pop them in the chat and ping me if I don't get back to you. But thank you very much for having me, SciFest Africa, and have a wonderful weekend.